For this video, we are going to focus on confidence intervals about a population mean. If you haven't seen the video on constructing confidence intervals about a population proportion, you should do that because it has a lot of necessary information with diagrams and so on, and it's explained in much more detail. For these problems, we're pretty much going to go through them quickly. They're very similar to the population proportion type of confidence intervals problems because basically we just find something called E, and we have a formula for it, and then we subtract E from something, and then on the other side we add E to something. So let's take a look at this problem 5. It says a particular Yanmar sailboat diesel engine specifications sheet claims that the engine can run for 10,000 hours with proper maintenance before a major rebuild becomes necessary. A survey was conducted on 65 randomly selected, well-maintained sailboat Yanmar engines of this type, and it was determined that the mean number of runtime hours before a rebuild became necessary was 9,320 hours. It is also known that the population standard deviation of runtime hours before a rebuild becomes necessary is 1,162 hours. With a 90% level of confidence, construct a confidence interval about the population mean number of hours necessary before a rebuild. That's supposed to say is necessary for this particular Yanmar engine. And then there's a second part to this. Does the 10,000 hours stated on the specs make sense? So I'll explain how we answer that after we get the confidence interval. Just like the population proportion type of problems, we first need to determine the correct sampling distribution. Since this is a problem for which we're asked to determine the confidence interval for a mean, we have a decision to make. In order to make that decision, the question we need to ask is sigma known? Meaning, are we given a population standard deviation in the problem? The answer to that for this problem is yes. It says right here, it is known that the population standard deviation, etc., is 1,162 hours. So we're given a population standard deviation. Since the answer to that question is yes, the correct sampling distribution is the standard normal, just like the population proportion problems. If the answer was no to that, we'll talk about it later, but we use the T distribution. It's actually called the student's T distribution, but we just abbreviate it as the T distribution. For this problem, we need to determine the following parameters. X bar, which is the sample mean for the problem, either sigma or S. So either the population standard deviation or the sample standard deviation. N, which is the number of measurements used, the number of people surveyed, number of engines in this case that are surveyed. A level of confidence, and just like everything else, if there's no level of confidence or level of significance given in the problem, then we default to 95%. This problem, they explicitly give us a confidence level right here, a 90% level of confidence, so we don't have to resort to the default. Okay, alpha, or the level of significance, and it's the complement of the level of confidence. Alpha over 2, just like before, self-explanatory. we divide the level of significance into two tails. Z sub alpha over 2. This is the exact same thing we used when we did population proportion confidence intervals as well. We use the norm.s.inv function. Nu, that's what this symbol is. This is Greek. This is the Greek letter nu, the lowercase Greek letter nu. And we use it to represent something we call degrees of freedom. I just love that. The calculation for nu is very simple. Nu is simply the number of measurements we have minus 1. In other words, for this problem, it says that 65 randomly selected, well-maintained sailboats. So that means that N is 65, but nu, or my degrees of freedom, is 64. It's that simple. And we also have this thing, if it's necessary to use it, if we're given S, or if we have to calculate S or approximate the standard deviation, then we find T sub alpha over 2. And again, this problem, we're given the population standard deviation, so we don't have to worry about the T sub alpha over 2. If we did, however, we would use the t.inv.2t alpha comma nu function, and we'll get to that. For this problem, then, we have x bar, or the sample mean, is 9,320. Sigma is equal to 1,162, and it's given to us. It's not S, it's a population standard deviation. N equals 65. My level of confidence is 0.90. Alpha is 0.10 because it's 1 minus my level of confidence. Alpha over 2 is just half of alpha. As it looks, it's 0.05. And I'll tell you Z sub alpha over 2 in a case like this is 1.645. The E formula is either, if sigma is given, it will be E equals Z sub alpha over 2 times sigma over the square root of n. A pretty simple one. Or, if sigma is not given, but we have a way of approximating it through S or another method, E would equal T sub alpha over 2 times S over the square root of n. So for this particular problem, E is equal to 1.645 times 1,162 over 65, which is approximately equal to 237.07. That's E. So once you get that, just like in the population proportion confidence interval problems, this becomes just a simple subtraction and then an addition. We take that E and we subtract it from x bar, and we say is less than or equal to mu, or my population mean, which is less than or equal to x bar plus E. Again, for this problem, that means we have 9,320 minus 237 is less than mu, which is less than 9,320 plus 237.07. And that basically means that mu falls somewhere between 9,083-ish and 9,557. To answer the second part of this, does it make sense that the rebuild would be necessary after about 10,000 hours? And the answer to that is really no. And the reason why is, with a 90% level of confidence, we can say that my population mean, mu, is between this 9082 or 3 number and 9557. If 10,000 had been in there, in other words, if this went from 9082 to 10,150 or something like that, then we could be 90% confident that that 10,000 would fall somewhere in there and they would be correct on the spec sheet. So if I go back up, I'll explain a little bit more what I mean. On the spec sheet, it said that it could run for 10,000 hours with proper maintenance before a major rebuild. But 10,000 hours does not fall in this range. That being said, it's close. And, what's the difference between, 9,500 and 10,000? It's just 500 hours. But it's still probably an improper thing to put on a spec sheet if it doesn't even fall in a 90% confidence interval. Let's go to spreadsheet mode and see what this all looks like on a spreadsheet. Here I have the spreadsheet set up. We have X bar equals 9,320. N is equal to 65. For this value, new, which we don't need for this particular problem, but we'll put it there just to make it more user-friendly so that we can use this for either if sigma is known or sigma is not known. As you can see here, I have this whole panel right here. If sigma is known, then we just look at this one and it'll do the correct calculation. If sigma is not known, it will automatically populate this area. I'll explain that again when we get to a problem when sigma is not known. But it's an easy calculation. We might as well just put it in. So this will equal n minus 1. And again, that's the calculation for new, otherwise known as our degrees of freedom. S, or sigma, is 1,162. That, again, is just given to us in the problem, and it is given to us as sigma. My level of confidence, 0.90. Alpha, well, that equals 1 minus, and we're going to always let our spreadsheet do that kind of work for us, so we only populate it with specific parameters. Alpha over 2, well, that equals alpha divided by 2. For this panel, right here, the one in greenish, we will say equals for sigma, and I'm just going to click on the cell that contains that. And again, I will explain this to you later and why I have it set up this way. It just makes this spreadsheet a more multi-purpose spreadsheet. We have z sub alpha over 2, and if you remember from last video, that equals norm.s.inv of alpha over 2, and it's going to give me the negative result. So I'm going to do that little trick I did last time and nest this within an absolute value. So it equals absolute value of norm.s.inv. I have an open parenthesis for the norm.s.inv function, close parenthesis for that, and now I'm going to close my parenthesis for the absolute value. And as I had shown on the problem sheet, that works out to be 1.645. And now we do our E calculation. The E calculation, if you remember, was sigma is known, z sub alpha over 2 times sigma over the square root of n. And one of the beautiful things about that is that the order of operations is pretty easy on that. It will automatically take that into account if you just type it in exactly that way. So we would type in equals z sub alpha over 2 times sigma, which I'm going to get from right here, over SQRT of n, enter. And there you see it, that 237.07, just like on the problem sheet. Now all I have to do is subtract this number from x bar on the left side of this, and take this and add it to x bar on the right side. So this is going to equal x bar minus that 237.07 number, and over here equals x bar plus that 237.07 number. And again, the meaning behind this is we can be 90% confident that the true population mean would fall somewhere between 9082.93 and 9557.07. So let's go to the next problem. So in this problem, it says a survey of 18 randomly selected households in Wynot, North Carolina. Yeah, that's actually a place, by the way. Showed that the mean household income in 2018 was $53,568 with a standard deviation of 7,528. Construct a confidence interval about the population mean household income in Wynot, North Carolina. Well, first thing to notice here is that there is no level of confidence given. So we default to 95% level of confidence, which means that we have an alpha of 0.05, alpha over 2.025, but you'll see what happens. Also, sigma is unknown. We're given a standard deviation, however, nowhere does it say that this is a population standard deviation. If you don't see the word population there, or you don't see a sigma equals, you assume that whatever you get, it's S, which is the sample standard deviation. So the correct sampling distribution for this one is the t distribution. In Excel, the correct function, as I stated previously, is t.inv.2t, and then it's just alpha comma new. One strange thing that I find in Excel is that we have the two-tailed function and we have the one-tailed function. And I wish they had done that with the norm.inv.s function, because it would just make things a lot easier when we transition into the t distribution, because a t distribution has one for one tail and two tail. So just know this, that we don't have to split alpha into the two tails, because this function automatically does it for us. In other words, we don't have to find alpha over 2, because when you just put alpha in here, it automatically will give us alpha over 2, and it gives us the positive result. And again, it's alpha comma new, so that's why on the spreadsheet I just had that new function there, the n minus 1. So for this problem, here's what we have. We have x bar, or the sample mean, is 53,568. S, or my sample standard deviation, is 7,528. N is equal to 18. There are 18 households surveyed. New is equal to 18 minus 1, or 17. My level of confidence is 0.95. Alpha equals 0.05. Alpha over 2 equals 0.025. But if we're not given our population standard deviation, as I said, the alpha over 2 part of this is not necessary. Yeah, we'll keep it on the spreadsheet, but it's just not necessary. And then t sub alpha over 2 is equal to t dot inv, that 2t of whatever my alpha is, comma, whatever new is, which was 17, and that's approximately equal to 2.109815578. And as I have said earlier, because sigma is not given to us in the problem, we use the formula E equals t sub alpha over 2 times s over the square root of n. And notice this is the square root of n, not the square root of new here. The only time we use new is when we're working with the t function itself on the spreadsheet. So this is over, as I said, the square root of n. If I plug the parameters into that, I would have e equals 2.1098 times the 7528 over the square root of 18, which comes out to be approximately 3,743.59. The confidence interval is, we take the sample mean that we were given in the problem, which is 53,568, and from that we subtract the 3,743. It's less than mu, and then we do the thing with addition, and we get the mean household income, the population mean income. We can be 95% confident that it falls between $49,824.41 and $57,311.59. And here is the conclusion. We can conclude that with a 95% level of confidence, the population mean household income in Wynot, North Carolina, is between these two numbers. Let's go to spreadsheet mode and see how we would pop that in on a spreadsheet. Let's put these numbers in. We have 53,568 for my X bar. N was only 18. It'll automatically populate new. My S or sigma, and in this case it's S, was 7,528. Level of confidence, that was not given to us, so we defaulted to the 0.95 or 95% level of confidence. And we have alpha is equal to 0.05, and alpha over 2, even though we don't need it, is 0.025. Because sigma is not known, I'm going to populate this with different information. This will be equal to, and I just go over here to the sigma or S, the standard deviation. It doesn't change. It's just that on the right-hand panel, the one in red, we call it an S rather than a sigma. My T sub alpha over 2, here is where that new function comes in handy. That will equal T dot inv dot, right here we have 2t. Let's see, the first thing it's asking for is the probability, and remember we just use alpha, comma, new, and that's right up here. It's in cell B5, and I close this, and this function automatically gives me the positive value. And it's positive 2.1 blah blah blah, same thing I had on the problem page. And now I do the E calculation, which is just as easy as doing it over here with sigma known. It's just we have different numbers. Equals T sub alpha over 2 times S divided by square root SQRT open parenthesis of N close parenthesis, press enter, and there we have that 3,743.58-ish number. In this cell, I'm going to take E, I'm going to subtract it from X bar, and in this cell, I am going to take E and add it to X bar, equals X bar minus E, and we have equals X bar plus E, and there I have the confidence interval. Because this one is in dollars, you probably would round down to the penny unless the problem specifically says otherwise, but I'm going to say it's between 49,824 and 41 cents, and over here $57,311.59. So this one had a lot of little quirks to it. Remember, we didn't have a confidence level given nor a level of significance, so we defaulted to the 0.95. Also, sigma was not known, but S was known, or the sample standard deviation. So we just used that, and that forced us to use the T distribution as the correct sampling distribution. The E calculation, pretty simple. And then we just subtracted from X bar and added to X bar. Let's take a look at problem number 7. A survey of 39 randomly selected new textbooks was conducted to determine price information. The prices for the textbooks went from $79.53 to $227.99, with a mean price of $129.98. With a 0.01 level of significance, construct a confidence interval about the mean population price of textbooks. Well, let's go over a few known things. For this problem, there is no level of confidence given. However, we are given a level of significance. Well, the level of significance is the complement of my level of confidence. What that means is if we have a 0.01 level of significance, I have a 0.99 level of confidence. In other words, level of significance is the same thing as your alpha value. This means that alpha is equal to 0.01, and the level of confidence is 99% or 0.99. Now notice that this problem does not have a population standard deviation, nor does it have a sample standard deviation. So what do we do? The only thing we can do is read into the problem and come up with an estimate for my standard deviation. And it's a very rough estimate, but we use it when we know some information and not other information. If you notice, the problem does say the prices range from $79.53 to $227.99. In a case such as this, we use something called the range rule of thumb to approximate the value for the standard deviation. The formula to do this is very, very simple. Basically, we subtract the smaller value in the range from the larger value in that range of prices that we do have. We get that result and divide that result by 4. Why 4? It doesn't really matter. We just divide by 4. So, in other words, an approximation for my standard deviation is the larger value minus the smaller value divided by 4. For this problem, it's 227.99 minus 79.53 over 4. That gives me an S of approximately 37.115 or $37.11.5. Being that we do not have a population standard deviation, we must use the t-distribution in this case. And if you notice, we are given a number of textbooks that we surveyed, which was 39. We have an X bar, or my sample mean, of $129.98. We have an approximation for my sample standard deviation of $37.11.5. We have n equal to 39, and since we're using the t-distribution, we need to find nu, which is 39 minus 1, or 38, with a level of confidence of 0.99. That means that my alpha is 0.01, which was actually given to us in the problem, and alpha over 2 is 0.005, but because we're using the t.inv.2t function, we do not necessarily need that alpha over 2 is 0.005. So t sub alpha over 2 will equal t.inv.2t of 0.01 comma 38, and it's approximately 2.7115. And just like all other confidence interval problems, we have to find E. And if you remember the formula for E, t sub alpha over 2 times S, or any approximation that I get for S, divided by the square root of n. And in this case, it comes out to be approximately 16.12. So since that's E, we subtract that value from my sample mean, and we add that value to my sample mean. We get that the confidence interval is $113.86 is less than mu, which is less than $146.10, which means we can be 99% confident that the population mean price of textbooks is somewhere between $113.86 and $146.10. Let's pop this on a spreadsheet. Here I have a spreadsheet that's set up specifically for when we're looking for a confidence interval and we have to use the range rule of thumb. I have X bar in here. I have n already here. This is taken directly from the problem. You can refer back to the problem. Remember, nu is just n minus 1, so that we'll just type in the formula. E, we click on whatever n is, and then we subtract 1 and press enter. I have my maximums and minimums switched, so let me fix that. We have a maximum data value of 227.99 and a minimum data value of $79.53. My level of confidence is 0.99. I know that they gave us alpha, but I always type in the level of confidence and I let the spreadsheet itself do the rest of the work. So alpha is equal to 1 minus whatever my level of confidence is. And alpha over 2, that just equals my alpha divided by 2. But remember, when we're using the range rule of thumb, the sampling distribution is the t-distribution, which means that we don't necessarily need the alpha over 2. It's calculated for us. To get my estimate of S using the RRT, or range rule of thumb, I type in equals, open parenthesis, I take my maximum data value. From that, I subtract my minimum data value. In other words, the range of prices. And I close my parenthesis, divided by 4, and enter. There we have that 37.115. To get t sub alpha over 2, we have equals t dot inv dot 2t of probability, that's what I call alpha, if you remember, comma, nu, or my degrees of freedom. And then I close my parenthesis and press enter. And there we have the 2.711 number. And now I calculate E. This is just as easy as everything that I did before. Equal t sub alpha over 2 times whatever approximation I have for S, and I divide it by the square root, which remember is SQRT, of N, and close my parenthesis, press enter, and that's where I got that 16.12 number. It's really 16.115 to 1099, but who cares? All I do from here is I take my X bar value and I subtract E. That goes on the left side, and X bar value plus E, that goes on the right hand side, equals X bar minus E equals X bar plus E. Here I have the numbers that basically I had before. This means that we can be 99% confident that the population mean price for textbooks is somewhere between $113.86 and $146.10 when I round this number here. Let's go to the next problem. Problem 8. A random sample of freshman students' combined SAT scores were collected at a competitive university. The data is shown below. Construct a confidence interval about the population mean SAT scores of freshman students at this university. So here's the data, 1210, 1360, 1250, etc., etc. What this means is we are given sample data for this problem. First, we have to determine the sample mean and the sample standard deviation. Once we get those two things, this problem becomes just like all the other ones that we've done so far as it pertains to finding the confidence interval about the mean. Hopefully by now you know the formula to get the mean average. Basically, all we do is add up all the data values that we're given and we divide by 11. We'll do this on a spreadsheet, and we'll do it even more easily than that because we'll just type in the numbers and use the equals average function. And we'll also get the standard deviation of a sample, so the stdev.s function, just like we did on the way earlier spreadsheets that we did. And I'll tell you now, we get S equals 104.194. Again, we're going to pop this all on a spreadsheet. I'm just sketching out the problem here. The correct sampling distribution is the t-distribution because, again, we're not given sigma. We're going to end up with a sample standard deviation, but that's S. We have X bar, and that we had to calculate, but it was 1321.818. My S was 104.194. N equals 11, so new is 11 minus 1, which equals 10. And my level of confidence, hey, that was not given in the problem, so we use the default of 95% level of confidence, which means alpha equals 0.05, and alpha over 2 is 0.025. T sub alpha over 2, remember the old t.inv.2t function, and that would be 0.05 comma 10 degrees of freedom, and that gives us this number here. And the E calculation is we take the t sub alpha over 2 times s over the square root of n, and that gives me approximately 70. What that means is the confidence interval is whatever my mean is minus 70, whatever my sample mean is plus 70, and it works out to be 1251.8 is less than mu, which is less than 1391.8. In other words, we can be 95% confident that the true population mean of the freshman class at this competitive university, that their combined SAT scores fall somewhere between 1251.8 and 1391.8. And that's basically what the conclusion is right over here. Let's go to a spreadsheet. Here I have a spreadsheet that's set up especially for this particular type of problem. I listed my data here, 1210, 1360, 1250, and so on. And you can check in the problem to make sure that that's all right. We have X bar equals, and well, X bar is the sample average, which equals AVER average. And I'm going to grab the first one and go down to the bottom one and close my parenthesis. Now make sure that when you're doing this problem, you if you have data, maybe you only have 6 data values. So make sure that you retype the whole formula for X bar over here equals average, and then drag and capture only the numbers that are for that problem. And if it has to go further than that, well then, make sure that you grab much further in the function. We have S equals, and well, that's the sample standard deviation, equals STDEV dot S. And again, I'm going to drag all of that or capture all of that, close, and press enter. Now, there's a number of ways you can get N. You can get it from, you could develop a formula to actually count those, but I'm not going to give you one that has a whole bunch of them where you'll end up miscounting, or at least I hope you won't miscount. So just count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So N equals 11. There's a good reason why I do this way, where I have X bar twice and I have N twice. It's because this will be, all of this stuff will draw from over here. I don't have another way of saying that, but it just makes things work out to be a lot nicer. So this will equal whatever I have for X bar over there. N will equal whatever I put for N over here. New, well, that's going to equal whatever I have for N minus 1. S, that will equal whatever I have for S. Level of confidence, This one was 0.95 because there was none given. And we have alpha, and alpha is equal to 1 minus whatever my level of confidence is. Now this is a little bit of overkill, but whatever. Equals S. Doesn't matter. I didn't really need to put that in there again. This is a remnant from a previous spreadsheet that I did. So T sub alpha over 2 is equal to T dot inv dot 2T of whatever alpha is, comma, whatever my degrees of freedom are, but that's new. E, remember the calculation for that. It equals my T sub alpha over 2 times my S divided by the SQRT of whatever N is. And close my parenthesis there and press enter. So I get 69.9998. So that's why I put 70 down, because pretty much wherever I round this, it's going to end up being 70. So that equals, we take X bar minus E and equals X bar plus E. And I have this confidence interval, which, if I were to put that in words, that the students in the freshman class at this competitive university had an average somewhere between 1251.8 and 1391.8 with a 95% level of confidence. Let's go to the next problem. The next problem is not a confidence interval problem. It's a minimum sample size, and we have minimum sample size for a mean. I'm only going to do one of these as it pertains to a mean. Basically, it's always the same thing, except if we are given a population standard deviation, we would use that. If we're given a sample standard deviation, we would use that one. But no matter what, we have to use the norm.s.inv function to do this, and not the t-distribution, because the t-distribution requires that we have a number of things already, which we don't have, and that's what we're looking for. So here's the problem. Assuming that the population standard deviation for Florida annual teachers' salaries is 1,964, determine the minimum sample size needed to be within $750 of the true population mean of Florida's teachers' salaries. We know that E is equal to Z sub alpha over 2 times sigma over the square root of n, or S over the square root of n. If we reverse engineer this formula, and I'm not going to go through all the algebra, we get n equals sigma times Z sub alpha over 2 all over E, and then we square that. If we happen to be given a sample standard deviation, it's pretty much the exact same thing. We just substitute this S here for where we had a sigma. Again, we have to use the standard normal for minimum sample size no matter what. And if we're not given a standard deviation at all, then what we will be given is something where you'd have to use another way to approximate a standard deviation, such as the range rule of thumb. So let's see what we have here. N, that's what we're looking for in this problem. E is 750. Y, remember the whole keyword thing. The keyword is to be within $750 of the mean salary of Florida teachers. So that within basically means that that's what my E is. We happen to be given a population standard deviation of 1,964, but even if we were given a sample standard deviation, we would do the problem the exact same way. Or if we weren't given either, then we would have to do it another way, and I can tell you that that other way will likely be by using the range rule of thumb. My level of confidence is 95% or 0.95. Why? Because it's not in the problem. So that's we use the default, which means my alpha is 0.05. Alpha over 2 is 0.025, which we will need for this problem because we're not using the t-distribution for this one. We're using the standard normal or z distribution. And I can tell you that z sub alpha over 2 will be equal to 1.96. Again, I'm going to pop this on a spreadsheet just like I always do. So, because of this formula up here, I have n equals 1964, which is my population standard deviation, times 1.96, which is my z sub alpha over 2. Multiply those together, divide by 750, get some number, and then square that. Well, that gives me approximately 26.34, but remember, this is n, and n has to be a positive integer. So this is saying that 26.34, 26 would not be enough teacher salaries to survey, but 27 would be, so we round up to 27, and that would be our answer. Let's go to spreadsheet mode. Okay, so here I have a spreadsheet all set up for us. We have E, remember that was 750. If you don't believe me, go back to the problem and check it out. Sigma or S, we were given that as 1,964. My level of confidence. Level of confidence was not given in the problem, so we default to 0.95. Alpha equals 1 minus my level of confidence. Alpha over 2 we actually need. We just say equals whatever we got for alpha divided by 2. And now z sub alpha over 2, remember the z function actually sometimes gives me the negative value. One thing to note is that when we go to the next part of this unit, the third video for this unit, we're going to do something called hypothesis testing, and we actually are sometimes going to use a negative value for z sub alpha, sometimes the positive value, and sometimes, well, basically both values. For confidence intervals, we always just use the positive one, which means I'm going to nest the norm.s.inv inside of an absolute value equals absolute value of norm.s.inv of alpha over 2. I close the norm.s.inv parenthesis, and remember that whole thing about it being red, so I'm just closing that one. And now I'm closing the absolute value one, and I am pressing enter. To calculate n, remember, I would have to multiply S or sigma times z sub alpha over 2, divide that by E, and then square that result. So equals, open parenthesis, my S or sigma times my z sub alpha over 2 divided by E, close parenthesis, and remember to get squared, I use the caret or shift 6, which means raised to the power of 2, and I get 26.34-ish. But that means that the minimum sample size will equal round up, open parenthesis, going to grab that n is greater than thing, comma, number of digits is 0, close parenthesis, and press enter, and there we have 27. And that is the answer. If you have to do one by the range rule of thumb, it's going to be the same thing. We're just going to have a maximum data value and a minimum data value. And over here, we would subtract the min from the max, get that result, divide that result by 4, and then we would just use whatever we get over here for my S or sigma in the function over here, or the formula over here. That's all for this video.